The semiconductor industry relies on a predictable progression. Manufacturers who purchase the most advanced hardware generally secure the highest market share. TSMC produces the majority of the world's leading-edge silicon, operating at a scale that dictates the global supply of high-performance processors. Despite this dominance, the company is choosing to bypass the immediate mass deployment of the most sophisticated lithography system ever built. This is the specification profile for ASML's TWINSCAN EXE5200B. It utilizes a 0.55 numerical aperture to achieve higher resolutions, but a single unit costs upwards of 350 million euros. While TSMC remains focused on their existing fleet, Intel is making an aggressive attempt to secure these machines in a bid to reclaim their position at the top of the foundry market. This delay is a specific mathematical calculation. TSMC's leadership has determined that the operational costs of this new architecture currently outweigh the potential gains in transistor density. The foundation of modern lithography was established decades ago through research at United States national laboratories. To create the light required for modern chips, a high-power laser strikes a microscopic droplet of liquid tin 50,000 times every second. This process generates a plasma that emits photons at a wavelength of exactly 13.5 nanometers. This wavelength represents a physical barrier. There is currently no practical method to generate shorter light, effectively trapping the entire industry at the 13.5 nanometer limit. Because the light itself cannot be shortened, engineers were forced to redesign the optical path to bend that light more aggressively, leading to a massive increase in mechanical complexity. The solution developed by Rayleigh is known as anamorphic projection optics, an intricate system involving an 8-mirror array. To maintain a high numerical aperture without building impossibly large mirrors, the lens applies asymmetric magnification. It shrinks the circuit pattern by 4 times in one direction, but 8 times in the other. This distortion allows the machine to focus the light onto much smaller features, but it fundamentally changes the geometry of the printing process. This squeeze has a permanent physical consequence. The area the machine can print on the silicon wafer is cut exactly in half. For manufacturers of large AI data center processors, this halved printing field creates an immediate and expensive bottleneck in production efficiency. Because the field is halved, large chip designs must be split into 2 separate exposures, a process known as the stitching tax. The alignment must be nearly perfect. If the 2 halves are offset by more than 2 nanometers, the connections between the circuits break and the entire wafer is lost. To make up for the lost time of printing in 2 stages, the internal components of the machine must move at extreme speeds, accelerating at 32 g-forces to maintain factory throughput. At this scale, the industry also faces the quantum limit of photon shot noise. There are simply not enough photons in this tiny space to consistently trigger the necessary chemical reactions. The result is a jagged, broken line that creates electrical shorts across the transistor gates. When the physical behavior of light becomes a matter of probability, the success of a fabrication plant relies increasingly on algorithmic software to correct for these hardware limitations. This shift requires computational lithography and machine learning proximity correction, complex software models that mathematically predict and compensate for the optical errors of the hardware. Running these models for billions of transistors requires massive server clusters, adding a significant computational layer to the manufacturing process. The total energy required for the lasers, the mechanical stages, and the server clusters is immense. A single TSMC fabrication facility now draws up to 200 megawatts of continuous power. The difficulty of manipulating light at the atomic level now has a direct impact on national electrical grids and regional environmental policy. Considering the high power draw and the risks of stitching errors, TSMC has concluded that staying with older, proven multi-patterning techniques is a more stable economic path. Meanwhile, Intel is attempting to use this transition to leapfrog the competition, betting that they can master these complex machines before the costs become unsustainable. Industrial leadership in this era depends on a manufacturer's ability to manage the yield losses and massive capital requirements inherent in this specific architecture. TSMC's decision suggests that the industry has reached a threshold where the mechanical and economic cost of shrinking transistors is beginning to outpace the commercial value they provide.